Hi everyone. In this video we are going to talk about the dehydration reaction of alcohols, which also belongs to the category which involves the cleavage of OH bond. Okay, sorry, carbon oxygen bond. So we are going to discuss dehydration. So what dehydration simply means, that is the removal of water. Okay, when we remove a molecule of water from the alcohol, we say that the alcohol has been dehydrated. And the reaction of dehydration of alcohol is done at high temperature in the presence of an acid as a catalyst in this reaction. Okay, so we use inorganic acids such as sulfuric acid or phosphoric acid, and we generate the alkene in this reaction. Okay, there is a removal of water molecule which results in the formation of an alkene. Okay, this is the simple example here. So we do this reaction in presence of an acid as a catalyst, and we do this reaction at high temperature. Temperature is needed in the reaction. Okay, we need a high temperature in the reaction. Okay, so the result is that we remove this water molecule, and there is a formation of a carbon carbon double bond. Okay, there is a formation of a double bond across the carbons. Okay, across the carbons, and we have to remember that the removal of water molecules from the adjacent carbons. Okay, this carbon and this is its adjacent carbon. There will be loss of hydrogen and hydroxyl group from these two adjacent carbons, and the result is an alkene. Okay, so this reaction which we call as the dehydration reaction, there is a different order for the feasibility of the reaction for different alcohols. Okay, if we look at these three examples, this is a primary alcohol, this is secondary alcohol, and this is a tertiary alcohol. For the dehydration of the primary alcohol, we are using the concentrated H2SO4. Okay, we are using concentrated H2SO4. That means we have not added any water in the acid. The acid is not diluted, and we have a very high temperature, 180 degrees Celsius, and the reaction is completed, and the formation of alkene there. Okay, when we do the reaction for the 2-degree alcohol, this is a secondary alcohol, we are using 85% of the acid. Okay, in this case we have shown the H3PO4. We can also use H2SO4. So 85% of means we have 15% of water in this acid. This is not concentrated, this is diluted, and the reaction is comparatively at lower temperature, and we're getting an alkene in this case also, and water is the byproduct. Okay, this is an example. We have, this is the tertiary alcohol. There are 3 CH3 groups attached to this carbon. This reaction takes place, dehydration of this alcohol takes place at 20% of the acid, and we are using only 85 degrees Celsius of temperature, and the reaction gets completed. So that's why we are saying that the ease of dehydration of alcohols follows the order, that is 3-degree alcohols are easily dehydrated as compared to the 2-degree, and 2-degree are easily dehydrated as compared to the primary alcohol. So this is the order of dehydration of the alcohols. Okay, so without giving the temperature, there will be no dehydration. For primary alcohols, we have this range of temperature from 170 to 180 degree, and for the 2-degree alcohol, this is the range, and for the 3-degree alcohols, the range is we're using very low temperature for the dehydration of the alcohols. So if we are not heating the reaction sufficiently, there will be no dehydration and no formation of alkenes. Okay, but react with alcohols will react with each other, and there will be the formation of ether if we are not giving the temperature to the reaction. So temperature is very important for the reaction, for the dehydration reaction of alcohols. Now talking about the mechanism of the reaction, the reaction is actually follows a E1 elimination reaction. Okay, this is the E1 mechanism, elimination. elimination, E1 elimination reaction. So this is the elimination reaction. Okay, so it follows the E1 mechanism but for the secondary and tertiary alcohols, and for the primary alcohols there is the E2 mechanism that we will discuss separately. So for the dehydration of secondary and tertiary alcohols, the reaction follows E1 mechanism. Okay, it follows the E1 mechanism. So what happens in the reaction is that we have the first step of the reaction. What's going to happen? There is the hydroxy oxygen. This hydroxy oxygen donates 2 electrons to a proton from the acid. Okay, there is actually abstraction of this proton. There is the abstraction of this proton from this acid. Okay, we are using H2SO4. This is H2SO4, and there is the abstraction of proton from the hydroxyl oxygen. That's why we are saying that the hydroxy oxygen donates a pair of electrons to the proton from the acid, and we are getting an oxonium ion. This is the oxonium ion formed. This is the oxonium ion. Okay, or we can more correctly say this is alkyl oxonium ion. This is alkyl oxonium ion. So in the next step, what happens in the next step? If you see that there is a positive charge on positive charge on this oxygen. This is formal 1 positive charge on this, and this is unstable in nature. So what happens? There will be this electron pair will transfer to the oxygen, and it will leave as water, and there will be the formation of a carbocation. Okay, we have formed a carbocation in this reaction. In this setup, the intermediate here is the carbocation. Okay. Now what happens in this next step? This is the water. Okay, this is water. The water abstracts the proton to neutralize this charge on the carbon. The water molecule in the reaction system abstracts the proton from the beta hydrogen. Okay, this is the beta carbon. Okay, this is actually the carbon. This carbon is alpha carbon because this carbon is directly attached to the hydroxyl group, and the next carbon to this carbon is beta. This is beta carbon. This is also beta carbon. So there is abstraction of the beta hydrogen from the carbocation that is formed. Okay, this water will abstract the proton. Now it has two ways to abstract the proton. Either it can abstract this beta hydrogen, or it can abstract this beta hydrogen. Okay, this is the color coded mechanism. We have shown color coded arrows here. This has a meaning. So if this pathway is followed, this black pathway, there will be abstraction of this proton, or there can be this pathway. The water molecule will abstract the proton from this beta hydrogen, because these are both beta hydrogens. So as a result, what's going to happen? If the black pathway is followed, so we are getting an alkene. This is the alkene. Okay, this is alkene, but this is alkene which is more substituted. This is more substituted alkene. Okay, now in this case, as we have this is butanol we had in the reaction, from which we have started the reaction. This butanol is converted into the butene. This is butene, but the double bond is at 2 carbon position. That is why we call this as 2-butene. Now this is the 2-butene which is formed if this pathway is formed. If this hydrogen is abstracted by the water, then the reaction product will be the 2-butene. And if this path is followed, this hydrogen is abstracted, then the product will be again an alkene, but this is 1-butene. The position of double bond at this in this product will be at this will be the terminal alkene. Okay, this is 1-butene, this is 2-butene. So actually what the alkene form depends on the proton that is abstracted. If we are abstracting the black if this path is followed, then 2 butene is formed, and if this path is followed, then 1 butene is formed. And if we look at this alkene, this is more substituted alkene. This has one methyl group on this side and another methyl on this side. Okay, so this alkene is substituted on both sides. This is more substituted alkene, and this is less substituted alkene. We don't have any other substitution on the other side of this alkene. Okay, this double bond here. So this is less substituted, and we know that the less substituted alkene is not stable, is not that much stable as compared to the more substituted alkenes. So more substituted alkenes are more stable than the less substituted alkenes. So in this reaction, the major product will be the 2-butene. Okay, again there is the possibility of two isomers of this 2-butene. It can be trans. Okay, the methyl groups are opposite to each other, so this is the trans alkene. And the product can be cis also, cis alkene. Okay, the methyl groups, the heavier groups, are on the same side of the double bond. If we make the comparison of the two, then trans is more stable than the cis. So the major product of this reaction will be the trans alkene, that is 2-butene. So in different situations, we have to look at the stability order, and we have to look at the stability of the product. The more stable product will be the final product and the major product of the reaction. Although the possibility of formation of both products is there, there will be the formation of both the products, but this product will be formed as a major product. Okay, so we have to this rule of formation of major product is explained by the Seit-Zeff's rule. Okay, we also write this as Seit-Zeff's rule. Okay, Seit-Zeff's, at many places will see it written like this, Sait-Zeffs. Okay, Seit-Zeff's rule, which again explains the stability of the more substituted alkenes. So according to this rule, the more substituted alkenes are formed preferentially because they are more stable than the less substituted alkenes. Okay, and additionally, that, as we already said, that trans alkenes are more stable than the cis alkenes and are also major product of this reaction. Okay, as in this case we have shown that the trans diastomer of the 2-butene is the major product of the reaction. Okay, now we'll be looking at the mechanism of the primary alcohols. So since this reaction is a concerted reaction, okay, it follows a concerted mechanism. This E2 mechanism is a concerted mechanism, that is bond making and breaking is simultaneous. Okay, so what happens in this is the alpha hydrogen, this is the beta, this is alpha carbon, this is beta carbon. Okay, these are beta hydrogens. So what happens, there is the abstraction of proton from the acid that we have used in the reaction. At temperature, what happens, there is the positive charge again on the oxygen, which is unstable, and this is the conjugate base of this acid, this strong acid. So it abstracts the proton from the beta proton from the carbon. Okay, as a result, there is a formation of double bond between these two carbons, and at the same time this molecule is kicked off as a water. Okay, as a water molecule. So this is a concerted mechanism. In concerted step, there is a dehydration of primary alcohol. This is the E2 mechanism. Okay, this is E2 mechanism. There is no formation of no intermediate, no carbocation is formed. There is a formation of carbocation in the E1 mechanism, and in this case we have formation of no carbocation, and the reaction is concerted. It goes in a single step. That's formation and breaking and making of bonds is happening simultaneously. Okay, it is happening simultaneously. As a result, we are getting this alkene as a product. Okay, and these are the byproducts of the reaction, and acid as a catalyst has come out as it was. Okay, so we have to remember some key points of the reaction. The reaction is a 1,2 elimination reaction, or we also call it as beta elimination, because there is the elimination of beta hydrogen. Okay, elimination of hydrogen from beta carbon. So that is why we also call it as beta elimination, or it's also called as 1,2 elimination. Okay, Next, when heated with strong acids, okay, commonly used acids are H2SO4, that is sulfuric acid, or we can use H3PO4. Okay, alcohols typically undergo uncountable elimination reactions, and we get the alkene as a product, and water is the byproduct. Okay, dehydration reaction it is. So water comes out in the reaction. And if we talk about the reactivity order, as we have already discussed it, this is the reactivity order of the alcohols, okay, towards the dehydration reaction. Many a times we get this question, okay. And if we talk about the regioselectivity, the major product is the more substituted alkene according to Zev's rule. Zev's rule, or Zev's rule we can also call it as. So according to this rule, the more substituted alkene is formed. Okay, this is because there is the possibility of abstraction of hydrogen from two beta carbons. So the abstraction is from the that carbon which results in the formation of more substituted alkene, as we have already seen. Okay, and if we talk about stereoselectivity, then trans isomer is formed in abundance than the cis product. Okay, and the reaction follows the even mechanism because there is the carbocation generation. And if we talk about the primary alcohols, it is E2 mechanism. Okay, since in this step even elimination we have the formation of the carbocation, so there is equal possibility of rearrangement. Okay, these points will be clear about these points in the practice problems, and we'll try to solve some practice problems on this reaction. These concepts will be cleared, and these are very important concepts as far as the questions for our competitive exam is concerned. Various questions are asked from this portion of the reaction. Okay, so we'll continue our discussion about the reactions of alcohols in our upcoming videos.